Okay, so far we have seen two rules, two you can call theorems about op amps. What are they? Input output relationship. If Vp is higher, output is positive. If Vn is higher, output is negative. Rule 2, no current goes into or out of the input terminals of an op amp. And in the next class we have seen three circuits, three amplifier circuits made up with op amps, namely difference amplifier, non-inverting amplifiers and inverting amplifier. Once again we said just remember one circuit and from that you can derive the other two. Okay? And never ever by mistake make this plus or minus symbol wrong. Okay, never swap this plus minus symbol. This is very crucial. I forgot to mention. So correct plus minus symbols at the inputs are very important. Otherwise the circuit will not work. You will not get correct answers in the exam. So plus minus symbol is something you must put correctly, and we will also see as we go on why so. Okay, so today we will analyze these circuits one by one rigorously. So please pay your attention. So let us start with maybe this one, non-inverting amplifier. Okay, so we will analyze non-inverting amplifier. So before that, let me just copy this circuit. So this is non-inverting amplifier. Now the question is, if I tell you the value of say V2, if V2 which is same as Vp, okay, because they are directly connected, if V2 which is same as Vp is given, I tell you that Vp is 5 volt, Vp is minus 2 volt, whatever, then Vo, that is output, is how much? So this is the question we are going to find. Okay. Now how to find this answer? So for that we have to use the input output relationship of an op amp, and the input output relationship, okay, is given by the static characteristic. So we have solution. So let's try the solution. So we have to use the static characteristic. Here x axis is what? Vp minus Vn, and this is Vo, and we know it looks like this. This part may or may not be a straight line. Okay, and this value is, if it has power supplies like V supply and minus V supply, then this point is V supply, this point is minus V supply. So this is the input output relationship. So if I know Vp, if I know Vn, then I can find the value of Vo, right? If I know Vp and Vn, then I can find Vo. Now Vp is given Do I know the value of Vn? No, Vn is not given to me directly. Okay, so to find Vo, we need Vp and Vn. Vn is given, sorry, Vp is given, but Vn equal to how much? But Vn is equal to how much? Do we know that? No. But we can say something about Vn. How? You see that this point is at potential Vo. This point is at potential 0. No current flows through this input, right? So if any current flows from here, it will go like this only, or it will go like this only. No current can bypass through this terminal. So the current can only flow like this. Nothing can go in this branch. Okay, I put a cross sign. So therefore Vn can be found out using potential divider rule. Again, this is Vo, this is 0, so Vn is somewhere in between. So I can write Vn is equal to, or before that, let me also write I. Maybe that will be easy. So this current I can write this is equal to Vo, this is Vo minus 0 divided by R1 plus R2. This is Vo by R1 plus R2. And therefore now Vn will be potential divider rule, R1 multiplied by I. R1 multiplied by I. So this is same as Vo by R1 plus R2 multiplied by, so this is I multiplied by R1. Okay, so this is Vn. So to know Vn, we need to know Vo. Okay, so that means to know Vn, we need to know Vo. And once again, here to know Vo, we need to know Vn. So it's a chicken and egg problem. To get output, we need Vn, and to find Vn, we need the output. It's a tough problem. I call it a chicken and egg problem. To find one, we need the other, but we do not have the other, because to find the other, we need the first one. Okay, so what is the solution? Can we not do anything? The solution is solve for Vn and Vo together, because there are two unknowns. We have two unknowns, namely Vn and Vo, and we also have two relationships between Vn and Vo. What are those two relationships? Number one, we can write from here. So this is one relationship. Okay, so we can write Vn is equal to this Vo R1 by R1 plus R2, or you can also write it this way: Vo is equal to Vn multiplied by R1 plus R2 whole divided by R1. Either way you can write. So this is one relationship between Vn and Vo, and second relationship is what is given by the static characteristic. So there is a relationship between Vn and Vo. So I write it. So this comes from the static characteristic. Okay, so you observe this relationship comes from the property of op amp and this comes from the external circuit, external to the op amp. Okay, so this relationship, this is nothing but the potential divider applied in this part of the circuit, R1 and R2. Okay, so this comes from the external circuitry. So we have two relationship, one from the op amp, one from the external part, and we have to now use them together to find Vn and Vo simultaneously. How? Okay. So here you see that Vp is given. Let me just copy this once again. So Vp is known, so it's a known value, it's like a known number. Okay, say Vp is equal to V2. Okay, so Vp is known. Vp is known equal to V2 sec. Okay, and Vn is unknown. Now what we will do, we will draw this graph in a slightly different way. How? Vo, here we will draw Vn minus Vp. Here it was Vp minus Vn, here we will draw Vn minus Vp. Now, so this will then look like this, opposite, right? So this is Vn minus Vp, and so also let's take an example that say this is equal to 5 volt. Okay, so if this is equal to 5 volt, then here we can write this is same as Vn minus 5 volt, right? Now we will modify this graph further. How? We will draw Vo versus Vn. So minus Vp is not there. So this part is not there. So only Vn. So how will this curve change? Okay. So you see that here at this point, what is the value of Vn? Here Vn minus Vp is 0, which means Vn equal to Vp, which means Vn equal to 5 volt. Okay, so this at this point Vn is equal to 5 volt, since Vn minus Vp is equal to 0 at this point. Okay, so that means at the value of 5 volt of Vn, this crossover occurs. So therefore in this curve, if I have 5 volt here somewhere, this is 0 volt, this is 5 volt, then this curve will shift like this. Okay, so now this is the curve for Vn versus output. So this is one relationship between Vn input and output, okay, which is coming from the static characteristic of op amp. And so this is relation 2, this relationship. And we have another relationship between Vn and Vo, which is here. Okay, so you observe Vo is Vn multiplied by some constant factor. Okay, so this is some constant factor 1 plus R2 by R1. So therefore we can draw this like a straight line passing through the origin. So let me draw this like this. Okay, so this is relation 1, this relation, this one. Okay, so now we have two relationships between Vo and Vn. One is this, another is this. So what will be the solution? So the solution will be definitely here at the intersection. So therefore this will be the solution. Okay, so this is how to find the solution. Now for an ideal op amp, we know that this static characteristic is very sharp, very vertical at this region or here. Okay, the resolution is very small, so the slope is very high, almost vertical. So therefore, so now let me just modify this. For an ideal op amp, okay, so for an ideal op amp, what is the modification I have to do? I have to make this line vertical as possible, and this, and I can erase the previous one. So now the solution will be at this point. So this is now the solution. Okay, so what is the solution? So the solution is that Vn at this point, Vn is equal to this value 5 volt. But what is this 5 volt? This 5 volt is nothing but the value of Vp. So, okay, so if you have written a general value Vp, this would have been Vp only. So you could just write this as Vp. 5 volt is just a specific example. In general, this is Vp. So therefore, it's better we write it, this is equal to Vp. So the solution is that Vn is equal to Vp. And how much is Vo? So now Vo, okay, so let's use this equation. Vo is Vn times this. And now let's put the value of Vn. So we have Vn is Vp. So we have R2 plus R1 by R1. So this is the solution. So this is the answer. Vo is this, Vn is this. So this is the answer. And this is how we can find the output for this circuit, this non inverting amplifier. Okay. Now let's take a pause and then think a few things. Firstly, আমি একটু পজ দিয়ে একটা জিনিস এঁকে নিচ্ছি। I have just copied this diagram once again here, and now I want to show what happens if you change the input. What is the input? The input is this value, okay, which is Vp. So if you change the input, what will change? This second relation, this will not change because this doesn't depend on Vp at all. But what will change is this red curve which comes from the static characteristic. Why will it change? Because the point at which this vertical line is there is at the value of Vn equal to Vp. If Vp is 5 volt, it will pass through this. If Vp is 3 volt, it will pass through this, and so on. Okay, so what happens, I'll show you through this animation. So if I say reduce Vp, then this red curve will be moved from right to left like this. Okay, and if it is moved here, so now this is Vp, then this point, okay, where my cursor is, will be the solution, will be the value of Vo. If I now increase the value of Vp, you see this red curve is moving towards the right, and therefore this crossing between the red and green curve is also moving towards the right and upwards. Okay, that means Vo is also increasing. So that's a nice observation. You see, if I reduce Vp, if I reduce input, output reduces. If I increase Vp, output increases, and it keeps increasing until at this point. After this, you see, output is not going to increase, because now the intersection of this green and the red curve is here at this saturation region, flat region. So even if I move this Vp further and further, the solution is at this point, which is constant, Vo equal to constant, and constant at the value, this is what? This is V supply plus V supply. So it's not going to change. Similarly, if I bring it down, down, at this moment output will be 0. I make it negative, output, you see, now the output is negative. Vp is negative, output is also negative. I make it further negative, and at some point, which is going beyond the limit of the screen, now you see that if I go further, the intersection will be here. So this is once again a saturation level. Okay, so output cannot go below this minus V supply or above this plus V supply. And if the input is within this region, starting from here, this is the maximum value to this somewhere here, where when this will intersect. So if the input is between this range, then output changes linearly proportionally with the input. Okay, so this is one observation. So let me write how in output changes with input, that is Vp or V2. Okay. Now next thing, let's discuss, let's observe that for this ideal op amp, okay, at the solution, that means at this crossing point, at the solution, this value of Vn is how much? It's a vertical line, so it's same as Vp. Okay, so here we have written it, Vn is equal to Vp. At the solution, Vn is equal to Vp. This happens because of the intersection of these two curves is at a point where Vn is equal to Vp. So this means as if the 2 points Vn and Vp in the circuit, so these 2 points, so they are at same potential, and when 2 points in a circuit are at same potential, it happens if those are electrically connected or sorted together, then it may happen. Okay, but here between these two Vn and Vp there is no connection at all, no short circuit at all, but yet they are at the same potential. So this fact is called a virtual sorting between Vn and Vp. Okay, so there is no actual sorting between Vn and Vp, not here, not even through the inside, I mean logically nothing there inside the op amp, because ideally no current goes like this or this, because here the current is 0, here the current is 0. So there is no actual sorting between these 2 points, yet they are at same potential, almost same potential, not at exact same potential, because this line is not exactly vertical, this is slightly tilted. Okay, how much tilted? That depends on how good the op amp is. For a perfect op amp, this is perfectly vertical, almost vertical. For good op amp, this is very much vertical. So therefore, this solution, okay, this is the solution. Now at this, so therefore this is the value of Vn, which is almost close to Vp, very close to Vp. Okay, so therefore for a good op amp, Vp is equal to Vn, or very close to, they are very close to each other. Okay, so therefore it's better if I put this. Okay, so this is called virtual sorting. This is not actual sorting because there is no connection between these 2 points. Okay, so let me zoom it in and tell you once again that there is no current here, so there is therefore no current at all here, or do not think that there is some current flowing like this from here to here or here to here. Okay, not at all. So this is called virtual sorting, and an important fact is that this virtual sorting is not a property of the op amp. Okay, so virtual sorting is not an property of the op amp. Rather, it's a property of the entire circuit, everything together. Okay, if you just have an op amp with say this resistance, these connections are not there, do not say that Vp and Vn will be always same. Okay, so but it is true for this particular circuit. So rather this is a property of this circuit, and it's also true for other some other circuit, but in general it is not true for all circuit. It is only true for some circuits and not for the op amp alone. Okay, so if you just have the op amp alone, do not ever without all these connections, it's not that these two terminals are going to have same potential. No. Okay, and also this is true only when Vp is within the limit of the saturation. Okay, so as we have seen, so if I increase Vp like this, so now Vp is this much. Okay, so Vp is here, now the solution will be here. Okay, and therefore Vn is here, so this is Vn, and Vp is here, so Vn and Vp are not same. So once the circuit saturates because input is too much high, then this virtual shorting is not going to be true. Okay, so that's about non-inverting amplifier. Next we shall see inverting amplifier. Thank you.